Okay, we're in Chapter 2, Section 5, Exponential Functions, and we're going to take a look at the first objective for this section, which is being able to graph and identify the properties of exponential functions. Well, what is an exponential function? This equation, f of x equals b to the power of x, where b is a number different than 1, defines an exponential function for each different constant b, which we call the base. The domain of this function is the set of all real numbers, because x here could be any real number, right? It represents a power, while the range of f is the set of all positive real numbers. We'll see that in a second. Okay, let's start with a riddle. Here's the problem related to exponential functions. Suppose you received a penny on the first day of December. Then you got 2 pennies on the second day of December, 4 pennies on the third day, 8 pennies on the fourth day, and so on. How many pennies would you receive on December 31st if this pattern continues? Would you rather take this amount of money or receive a lump sum payment of $10 million? We'll tell you something. This is a trick question. Let's see why. Why don't we complete this table here? So here's the days, right? Day number 1 is December 1st. This is December 2nd, etc. Right? It goes on. So on December 1st, I get 1 penny. On December 2nd, I get 2 pennies. Then it doubles. On December 3, I get 4 pennies. 8 pennies on the 4th day. 16 on December 5th. 32 on December 6th. 64 on December 7th. Now notice, I'm going to look for a pattern here, and since the number of pennies doubles from day to day, I'm going to try to see if this pattern has something to do with base 2. In other words, multiplication of 2. And sure enough, it does, because 2 could be written, the number of pennies on day 2, could be written as 2 to the first power. 4, the number of pennies on day 3, can be written as 2 squared. 8, the number of pennies on day 4, could be written as 2 cubed. And I could keep this up, 2 to the 4th, 2 to the 5th, 2 to the 6th. That will just give me the number of pennies on whatever the day is, right? And how do I find the day? I just add 1 to my power, right? In other words, the power is the day minus 1, if you want to think about it that way. Well, then the question to ask is, if this continued, how many pennies would you have on December 31st? And since this is 31 days after you started, the answer should be 2 to the 30th power. 2 raised to the 30th power. Okay, well, what is 2 to the 30th power? That turns out to be this number. Okay, 1,073,741,824 pennies. Now, we want to know what this amount is in dollars, so we move the decimal point 2 places to the left, and we find that, are you ready? You should get $10,737,418.24. Not bad for starting out with 1 penny. Well, the obvious answer to the question then is to take the number of pennies on December 31st, and not a lump sum payment of 10 million. But to be honest, I wouldn't mind having either amount. Either way, the example shows how an exponential function grows extremely rapidly. It changes very quick. In this case, the exponential function was 2 to the x, and that's what we used to model the problem, because the number of pennies doubled with every consecutive day. Okay, why don't we take a look at graphing this exponential function, 2 to the x. How can we do it? Well, one way to do it is the way we graph functions earlier in this chapter. That's to use a table, right? So x here is a real number, right? Remember, the domain of these functions, of these exponential functions, are the set of real numbers. So the domain is the set of real numbers. So x is a real number that you could replace with with square root of 2, pi, any other irrational number if you want, because it's a real number. We'll use integer values to make life easier for x in our table. So here's what our table and graph look like. So we started at -4 and kept adding 1 up to 2, and then you see the output. So if x is -4, I get 2 to the -4 power, which hopefully you remember from Algebra 2. Anytime you have a negative power, this just means 1 over the same base, 2 in this case, to that number being positive now, to that power being positive, 4. So this is 1 over 2 to the 4th, which is 1 over 16. Likewise, 2 to the -3 is 1 over 2 cubed, which is 8. So you get 1 over 8. 1/4, 1/2. So these are very, very small numbers. So when this is negative, when x is negative, the outputs are very small. Notice they're right above the x-axis, very close to it. And then look how rapidly it changes. At 0 we're at 1. At 1 we're at 2. At 2 we jump to 4. And then if we were to keep going, at 3 we would jump all the way to 8. At 4 we jump all the way to 16 up here. So this function changes very rapidly for positive inputs. Okay, well, this happens to be a general property of these exponential functions. Here's some other basic properties for the graph of f of x equals b to the power of x. The base we take is always going to be bigger than 0 and different than 1, right? Don't forget that. So all graphs will pass through 0, 1. That's the y-intercept. Why? Because any number raised to the 0th power when x is 0 is going to be 1, right? Any number bigger than 0 and different than 1 raised to the 0th power will be 1. That's the reason. Also notice all graphs are continuous curves with no holes or jumps. You could trace the graph without lifting your pencil up from the paper. The x-axis will always be a horizontal asymptote. So you might have noticed for the graph, let me back up here, of 2 to the x, as I said, we get very, very small when x is negative, and it seems like we're touching the x-axis, but really we're not. We're right above it. We're never ever going to hit the x-axis. We're never ever going to equal to 0. Why is that? Because no positive number, or as a matter of fact negative number, raised to any power will give you 0, right? Raising a number to a power will never give you 0, because the power just tells you multiply that base by itself x many times. And multiplying any number other than 0 x many times by itself does not produce 0. Okay, so that's why the x-axis is a horizontal asymptote here. We're never going to get 0. Let's see. If b is bigger than 1, then b to the power of x increases as x increases. If b is between 0 and 1, then b to the power of x decreases as x increases. Okay, so another couple examples here. Here's a graph of f of x equals 2 to the negative x. So we have a negative exponent. Again, the best thing to do is just change this to 1 over 2 to the x. So once again, using a table of values, you can get a graph going. And notice you'll obtain the following graph, which looks like the reflection of what we had earlier, right? Which was the graph of y equals 2 to the x. Let me try and make this a little nicer here. So something like this. This was y equals 2 to the x. This is y equals 2 to the negative x. So notice the graphs of b to the x and b to the negative x will simply be reflections of each other about the y-axis in general. That's a very helpful fact to know. So please take a note of that. Okay, now graphing other exponential functions. How about 3 to the x, you might be wondering. Well, just as before, construct a table of values, plot a few points, and you're going to get that same pattern curve. So be careful not to assume the graph crosses the negative x-axis, right? Remember, it gets close, but never intersects it. So here's a few points that you could plot, right? At 0, it's 1. At 1, it's 3. At 2 is 8. At negative 1, it's 1/3. And at negative 2, it's 1/9. So pretty close. And here it is graphed using Excel. So that's y equals 3 to the x. And that's graphing another type. So for other exponential graphs, here's an example of 4 to the negative x. Once again, note it's a reflection of f of x equals 4 to the x, which if we were to graph right here, it would look something like this, right? Just a reflection over the y-axis. This function, the blue one, 4 to the negative x, is always decreasing. It's always getting smaller, right? You start up here, and your y values are getting smaller and smaller as x increases. This passes through 0, 1 for the same reason as earlier. 4 to the power of 0 is 1. Okay, so some properties of exponential functions that hopefully you remember from Algebra 2. You can pause the slide if you want, pause the video here, and see if you remember these. We have the exponent laws, that tells you if you have the same base, different powers, and you're multiplying, and you can add the powers. The quotient law, which tells you if you're dividing, you subtract. The power to a power rule, that tells you multiply the powers. Product to a power, which means you distribute the power to each multiple inside. And quotient to a power, which means that you put each numerator and denominator, you put each part of the quotient to that power x. Further, recall a to the x equals a to the y, if and only if x is equal to y. Very important when we solve equations. And then for x different than 0, a to the x equals b to the x happens if and only if a is equal to b. So take a second, pause this video here if you'd like, and take a look at this slide, read your book again, and make sure you remember all these rules.